I'm Gwen Shapira. אתם יכולים לקרוא לי חן. I've been moving data from here to there for the last 15 years. So I started with relational databases. I did a lot of Oracle. I did RAC and Exadata implementations as a consultant. And then my customers started moving to Hadoop. And after about a year of helping customers integrate Oracle with Hadoop, I figured out that there is a trend there and just moved to Cloudera to help customers do Hadoop full time. I was a consultant for Cloudera, but a few months ago I decided that I'm done with traveling. I don't want any airline mileage anymore. And I'm now a developer. So I contribute to Scoop, Kafka, Flume. Everything that moves data from somewhere into Hadoop is stuff that I'm doing. I'm on Twitter. I tweet a lot. If you want to drown in big data snippets and news and thoughts and bits, you can follow me on Twitter. I wrote a book with 3 of my colleagues. It has a lot of tips on how to use Hadoop in production, what are the best practices when developing, how to choose components, which data types, all kind of stuff. This presentation is a bunch of tips that I thought of or learned or came up after the book was already done. So it's kind of the preparation for the next release, I guess. So talking about agile data systems, what is it that makes the data system agile? Well, when I worked with Hadoop customers, we used to build something. And it's a POC. You have about a month, so you build something super specific. We get data from this system. We do this transformation. The result is over there. You do this type of analysis. It's very nice, but it's also super fragile. It's not going to survive any change. So adding data would be super difficult. Doing different types of analytics will require doing the whole thing from scratch, basically. So after a while, it kind of felt like I'm tricking my customers. They think that this Hadoop is an awesome thing because I show them really quickly how awesome it is. I leave, and they're there with a system that is not going to be able to move forward at all. So the opposite is agile systems, where you can add data and analytics really quickly, just new data sources or new types of analysis, and you don't risk anything. You can add a new data source without saying, oh my God, it's going to break all this stuff at the other end. If you made a mistake because you want to move fast, you want to add new types of analysis, maybe the code you added is not perfect. Maybe you process data in a way that created something that is a bit less than awesome. Well, we want to have a system where you can easily recover from mistakes, so moving fast is not that risky anymore. So I'm going to bring up 4 different patterns that I've seen in my work that help people build systems that are agile and are extensible. And I'm going to talk for a few minutes on each. And if one of them looks to you like, oh, that's a pattern, I mean, what's the big deal? Remember, first of all, that singleton is a pattern. And it's just a global variable, but it is also known as a pattern. So patterns don't have to be rocket science, first. And second, for each of those, there was at least one company where people were like, oh, I never thought of this before, oh my God, even though it looked obvious to me and obvious to everyone else. So just keep that in mind. And we'll start with the data bus, which is kind of a generic enterprise pattern that applies really, really well on big data systems. And here's the story. You start with something like that. Maybe you have some logs that you need to store in Hadoop. And you just write something that gets data, say Flume, gets data from some logs, puts them in Hadoop. Really, really simple. And then if the experiment was successful, you have a lot of more things that you want to do with Hadoop. And you start bringing them in. And it's all custom, right? You have some scope for a relational database. Maybe you build something that gets web clicks from your application. You have all those custom pipelines. But obviously, Hadoop is not the only thing that you have on your system. You're going to have relational database, a data warehouse, search applications, et cetera, et cetera, et cetera. You have a huge mess. And obviously, that's not half of it. Secretly, everything talks to everything in an organization. You always have some type of data over here that you need over there. And it gets really messy. And the worst thing is that it really adds a tax on the organization. Every time you need to add a new system, say I want to add a new web page in my site, you need to figure out how to integrate it with all those different backends. So maybe 10% more development. It's not a huge deal. But you have to pay in a week or 2 of development time every time you add a new system. So suddenly the whole promise of big data and integration and analytics becomes a huge drain on everything. And we don't really want that. We want people to be able to add new systems without paying extra taxes for it. So we really need a shared infrastructure that will make it really easy to send records, and we make it really easy to consume records, make it very risk-free, and we want to make sure that it scales. So obviously you have big data. Some of the systems may send millions of messages per second. It has to be able to grow that way. And you also have to make sure that the system sending data and the systems reading data can talk to each other. So we need some kind of record schema to make sure that they can read and write the same data, and they don't have to, people don't have to go ask, what is this thing in the 5th record of this type of data? And that's where we put Kafka. So I'm kind of a Kafka expert. That's has been my role for the last year or so. But I'm not going to tell you what is Kafka. There is enough stuff about it on the web, stuff I wrote, stuff that the Kafka team from LinkedIn wrote. But the idea is that it's a publish-subscribe system, kind of like ActiveMQ, RabbitMQ, MQ series, all that kind of thing. Except that it scales really, really well, both in terms of how much data you can pipe through it, in terms of how much you can safely keep historical data, and how many producers and consumers you can connect to it. So we really, really like using it. But obviously, if you happen to not have really big data, using different types of systems is fine, as long as you really decouple the producers of the data from the consumers. That's the importance of the pattern. So you can add new data sources without having to change anything in the consumers, or you can add new analytics without having to change anything in the producers. Next pattern is keep all data. And that's where my customers used to kind of look at me like, it looks self-serving. We are, after all, selling data by the node. You can only store that many terabytes on each node. If I tell you to keep a lot of data, it looks very self-serving. But it's actually useful, in addition to helping me get my salary on time. So the way traditionally in ETL we look at data, we say that we have all those input data. We have some kind of a pipeline analyzing the data, and we have the outputs. The inputs are obviously important. Those are applications. The outputs are important. Those are our analysis. That's the precious insights we worked hard for. Everything in between is kind of a waste of disk space, and we immediately throw it away. Except that that's not actually how we want to look at the data. That doesn't make any sense. Because all the in-between stages are either sources for some kind of an application that can use them. So alerts, for example, can start being fired off data before it went through a lot of processing and aggregation. So you can actually have more real-time system in there. You can get some kind of insights of data in between stages of the analytics. But also, if there was an error somewhere in the pipeline, you want to be able to go back and trace it and not have to reprocess everything from scratch. Just go, OK, this stage was fine, this stage was fine. That's where the problem was. Let's start reprocessing from that point. It can save you tons of time, obviously. Some of these stages can take a while. But it also means that you have the ability to debug and to understand your system and to figure out what caused the problems. We see it as super important. And since we just said that we have this data bus and we send everything to this data bus, well, in Kafka, and like every message queue in the world, you have topics, or some message queues call them queues, but it's more or less the same thing. Producers send data to all those different topics. They choose which topics they write the data to. Consumers subscribe to a topic and read data from the topic. Kafka is scalable, so each topic has multiple partitions to it, and you can subscribe to only some of the partitions. And the idea is that if you have in-between stages of analysis, you can actually just create topics for those in-between sessions. And so you actually pipe the data from topic to topic. And if someone is interested in an in-between stage, in the middle of the analysis, it just connects directly to the relevant topic and gets data from that topic. If you are interested in reprocessing because you think there was a mistake, you connect to that topic and start reprocessing from that point. So it's basically fairly straightforward. It's something that we did in HDFS or in databases. You have staging tables or you have staging directories in HDFS. Same thing, only with topics because we have more real-time streaming pipelines. The benefits, well, you can recover from accidents, as we said. You can do debug if something strange happened. You don't like, why is this number that way? You can go back and fix it. And you can also experiment, because you can subscribe to a topic with data you're interested in and create a whole new pipeline based on that topic without any change to anything that is already working. So that's basically the big benefit here. I don't know if it's a big deal in Israel, but when I was speaking both in San Jose and in London, everyone was talking about Lambda architecture versus Kappa architecture, and I think I even saw a session about it here, so I guess it is a big deal. Yes, so a lot of my customers for the last year have been trying to do Lambda architecture. I hate talking about it. I don't like giving a name to a high-level concept and saying this is this, when there's so many variants in between. I prefer talking about specifics. But when we look at what's common to all those Lambda architectures, well, they combine streaming and batches, and that's awesome. You get some real-time benefits from the stream, but also processing data in batch is pretty awesome in itself. You get scalability, which is also always something we like when we have a lot of data, and you can reprocess the data, which is the big deal. That's what we really want to be able to do, is try different types of processing. What nobody really likes is having two applications that do the exact same thing in two different code bases, sometimes in two different languages. So because maintaining two applications that do the same thing and they inevitably diverge and it's a pain in the ass, we have pain avoidance techniques. And one of them is to basically use the same language and same framework for streaming and batch. And I like Spark a lot, basically because I used to work in MapReduce, and Spark is like breath of fresh air. Suddenly things are fast, and I don't write to disk anymore, and I don't run out of I/O, and I don't saturate networks. It's like MapReduce, only you can actually cache data in memory, and you can build more complex graphs. So it has a nice API. It's much more fun to work with. If you didn't try if you do MapReduce and Hadoop and you didn't try writing code in Spark, you absolutely should. It's like, oh my God, I can get so much done in like 3 lines of code, and it can be Python, and it can be Scala, and I feel so productive again. It's awesome. So I like Spark a lot, and Spark has Spark streaming, so you can actually take the same code that you wrote in Spark and apply it to a stream, which is really, really great. There's other systems like that. When I wrote those slides, Spark was pretty much the only one. These days, Storm has Algebird from Twitter, so you can actually write MapReduce code and Spark code and Storm code that uses the same libraries, which is pretty cool. Flink does more or less the same thing. I mean, conceptually the same things. It has different implementation. All those are really cool systems. So as I said, Spark streaming is basically calling Spark in a loop. So you get a small batch of data, you process it again and again. So you can actually take the same code that you wrote for batch processing and apply it for stream. The other pattern, which is more of a Kappa architecture, is to say, hey, we don't actually need batch. I mean, batching can be very efficient in terms of economy of scale and in terms of how many machines they need to achieve the same thing. But for a lot of other things, like fixing errors or delayed arrivals and a lot of other stuff that traditionally we needed a batch, we don't really need batch. We can just go to Kafka and say, please replay the entire stream of data from the last week, month, year, and we will fix the errors on the fly from the stream directly. We don't need to go to any HDFS and batch process the data in order to fix errors. So for example, we say that we have a new algorithm and we want to try the new algorithm instead of the old one, and we really need to have a migration strategy. So instead of taking all the old data, reprocessing with the new algorithm, and then starting to catch up on streaming, obviously from an entirely new code base that was not tested until now, instead you have 2 streams, and you connect the new stream with the new algorithm to the beginning of the Kafka topic that stores all your data since last 3 months, the beginning of time, whatever. And you kind of process them in parallel, and you can check the data. Does it make sense? Doesn't it make sense? Tweak the new algorithm on real data. Slowly it catches up. It starts running on existing data, so you can actually see in real time whether they're the same or not. And then you switch. At some point you say, I like the results of the new algorithm better. Let's point my production application to the new stream of data. That's it. And when you do it, you're actually sure that you're getting good results. That reduces the risk. So you have the agile thing of trying stuff and reducing risk at the same time. What if your data arrives late? That's super common in telecoms, where a cell tower went down, so the cell tower cannot tell you that there are issues because it doesn't send anything. And then everyone connected to the cell tower, and you want to send their sensor data and location and everything, that will arrive late as well. So what do if you actually got a lot of data for yesterday? You basically start a new stream of data just to fix the new stream of processing, just to fix the data from yesterday. It's kind of, you have two streams in parallel, one that continues working on new data, working on whatever is relevant right now, so you still have your real-time processing, alerts, whatever you need, and you have something that fixes all data for you and writes it to the other partition in the database. And something that I've noticed when I talk to customers is that when I talk to them about real-time, well, they say things like, well, we need a real-time system. It has to give us something that is updated every 15 minutes. And I'm like, OK, 15 minutes is easy. You don't even need anything that I would call real-time. It's just batching only with faster batches. 5 minutes, sometimes faster batches will fit 5 minutes. That's more trickier. And then when you go below a minute, maybe you need to start having micro batches. So 30-second micro batch. And then when you go below a second, it's actually real time. So it's very difficult to get less than half a second in any type of micro batches. We start actually looking at each event on its own. So you have this continuum where things from 2 milliseconds to 15 minutes. And we don't want to say that this is batch and this is streaming, because you have all these things in between. We want to just say this is our system. And our batches get smaller and smaller, and the system is less and less efficient, but we can still scale it, so we can make up for the inefficiency, but it's more and more real time. Last tip, and that's like, schemas used to be completely non-controversial. Everyone had a schema. And now I'm feeling like I'm an iconoclast when I go to people and say, oh, you actually need a schema. I don't care if your data is unstructured. I don't care if it's semi-structured. I don't care what. You are going to have a schema. And I really believe that it's a must-have. And Cloudera kind of sells the whole schema on read thing. And I risk my job continuously when I tell people that schema on read is kind of a bullshit thing. So yes, sometimes you actually need to write logs somewhere and you don't know what the schema is. But after about a week with this data, you know exactly what the data is like. And if at that point you don't convert all the data to something that stores the schema somewhere and records exactly what the data is like, you are actually being lazy. You're saying, OK, I'll save time when reading the data and waste time of everyone who is, I'll save time when writing the data to Hadoop and waste time of everyone who has to read it, because they have to go and figure out what the data actually means from scratch. And when you do analytics, you have to know what the data means. The fields are important. You also waste a lot of space, because storing everything is in string when it's actually integers and longs and decimals is also a waste of disk space. So you waste people's time. You waste a lot of disk space. You make everything slower. And for what? Because you're too lazy to actually store the schema when you figured it out. So try to get a schema as close as possible to the point of integration. Everyone downstream will thank you later. Remember that there are usually a lot more programs reading the data than writing it if you are doing things right. Obviously, sometimes you write it and nobody actually cares. In this case, you don't need a schema. And that's important for integration, because we want a lot of producers, a lot of consumers that are decoupled from each other, that actually don't have to talk to each other and don't have to know about each other. It means that if my producer is adding a new field, I don't want every consumer to have to upgrade at the same time. In large organizations, it's impossible to upgrade every single application at the same time. I mean, let's take 500 people and everyone jump. Not going to work, ever. It's ridiculous. So we needed a way to add new fields and modify the schema, and having a schema is the way to do it. That's how consumers will know that the new data is something they can ignore. And there is a lot of way to actually have a schema. So the primitive one is people walk around and say, hey, we have this topic blah, and we have those messages. What does the fifth field mean? Happens a lot when we have JSON. And then if you're a bit smarter about it and you figure out that this is a waste of time, you may have some shared library with utility code for reading and writing every message. That's not bad, but we can do better. We can put a schema in every message if you use something like Avro, Thrift, Protobuf, etc. Or you can do even better than that and save on space because the schema is not going to change all that often, and have a centralized repository for schemas and just have a schema ID on messages or topics. And a very smart guy who does data analysis in Twitter said that, yes, schemas do make you move slower in the same way that stoplights make you move slower. If you're alone on Ayalon at 4 a.m., you probably don't need stoplights. If you are in a very busy street, well, it's Israel, you probably don't need stoplights either. But in normal countries, it's actually pretty helpful. So, and if you leave out your favorite DBA and how difficult it may or may not be to talk to your favorite DBAs, schemas are very agile. They can evolve, they allow you to add fields, they allow you to modify the data, they allow you to add readers and writers easily. It allows you to validate the data after it's written, so you can actually reduce risk by doing validation. It's actually pretty important. And I can't believe it, but I actually finished early, right? Oh my God.